Greetings and welcome in this my lecture on SymPy. SymPy is an open source Python library for symbolic mathematics. It is designed to perform symbolic mathematics tasks such as algebraic manipulation, calculus, equation solving, and more. Unlike numerical libraries that deals with the specific numerical values, SymPy focus on manipulating and working with symbolic expression, equations, and mathematical concept. In this lecture, we are covering the calculus part by using SymPy. This is my desktop and we will use here live shell for SymPy. So you will use the URL live.sympy.org. So this is the official SymPy official website which is live.sympy.org. When you will use this link URL, SymPy live shell will open and we can use directly in our system. You can use any system. SymPy live shell not required to install in any device. So this will work in cloud. When you will open this live shell, then these statement must appear before starting. On the very first you can see WebAssembly powered Python kernel backed by Pyodite. Then we have the very first statement from SymPy import. So when you will use SymPy library in Python, we always need to import the library, and the same is used at this place. Then we have initial printings. This statement is used for the printing of the statement at this place, and then we need to declare some variables for our current work. By default, when you will open this live shell, these statement will appear. If you want to increase the font size, press Control plus Shift plus plus, then you can see the font size increased. In the third statement, we can declare the integers. Symbol function is always used here to declare the variable, to declare functions, to declare integers, etc. So kmn is equal to we can declare multiple variable, integers, and functions by separating comma. As you can see here, k comma m comma n is equal to symbols, and in the quote sign there will be space between these integers, k space m space n, and you will make here integer is equal to true. So these integers will be declared. After that, we need some functions. To define the functions, we are using the same procedure, but at this place we have only CLS for calculus is equal to function. So these are the required variable, integers, and functions which we need for the present computation. So now the thing is how we can use the calculation at this place. If you have f is equal to, we are taking here simple function f is equal to sine x, and for the exponent we will use this product sign 2 times, and when you will enter, so you can see at the top this is the statement which we insert at this place. Now if you want to print again, enter f here, and you will see that the above statement converted into the symbolic form. So this is the statement in the Python. One more important thing, the SymPy is completely based on the Python. So all the syntax which we use in the Python, the same is we are using in the SymPy live shell. So the SymPy library completely built by using Python. This f will print the above statement, and as you can see, x double product 3 is x cube. So this product sign 2 times will represent exponent whenever you need, and if you are using the single product sign, that will be for product. Now if you want to operate some operations, so in this session we will cover differentiation, integration, and limits. These 3 things will be covered for calculus in this lecture. Now if you want to differentiate, if is inbuilt function in the Python, and you can use for differentiate diff f comma x, and then enter. So you can see that the derivative of the above statement is at this place, which is 3x square cos x cube. If you want a second order derivative, if you are using laptop or PC, then you can press upward arrow sign and the previous statement will appear at the cursor place. Introduce one more variable x. And so you can see we are differentiating f with respect to x 2 times. When we are using x 2 times, this will be the second order derivative. When you will enter and you will find that this is the second order derivative of the above function f. Similarly, as soon as you will increase the x variable, the order of the function derivative will be increased. So this will be the third order derivative of the function. The other way, if you are using at this place 2, then enter and you will find that the derivative which we find at this place diff f comma x, which is the second order derivative, and this is also the second order derivative, and the value of these two functions are same. You can see this equation as well as this one. So you can use numbers for the order of derivative, as you can see at this place. Again, if you need to find out the fifth order derivative, change the number, and when you will enter, you will get to the fifth order derivative of the above function. So in this way, you can find the derivative of any order of the function. Also, you can directly use the function like in this way. Diff, here I have sine x. I am using here sine x, and then comma x. So this will also will return the derivative of the function. So there are two different ways to use the function for derivative. If you have here is x cube and then enter. So in this way you can use to find out the derivative of any function. Now if we have f is equal to, I am using sine x cube, this is x cube, then I have a product and cos x. So this is the product of two functions, and then enter. If you want to print, then again enter f. So the above function will be printed or return the value in the symbolic form. Now deri is equal to, this is the just assignment for the variable, and then we have derivative, and here we are using f comma x, okay, and then enter. So the right hand side, the information which we enter in this equation will be stored in the left hand side, which is der. Okay, so now if you will again enter der, and the meaning of this statement will print at this place. This is the first order derivative of the function f, which we choose at this place. If you are using comma 3, then this will be the third order derivative of the function, and you can see in the symbolic form this will return the value. If you want to find out the value after simplification, or if you want to implement or this operator, for that what you will do, you will use here der dot do it function. So what will do this function? Do it will simplify the above equation and return the value c. So here you can see the derivative of above function, which is third order derivative. We have the corresponding value after simplification. So do it function will be used to simplify. If you have the derivative, you have integration, you have limit. For all the cases, we always use do it for the further simplification. Now if you want to find out the partial derivative of any function, see, I am choosing here f is equal to, I have is, sorry, f is equal to sine, and I am taking at its place x square plus y square plus z square. So I am choosing here three variables, and product exp, exponential x. Okay, so here I am using these two function and then enter. There is some error. Okay, the statement at this place 2 is missing. Now you can see the error invalid syntax, because this exponent was missing. That's why we have the error. When you will enter, yes, again to print the value, enter f at its place, and you can see that this is the function which we insert in the form of Python syntax. Now we want to find out the partial derivative. For partial derivative also we are using the same function, diff. So diff f comma x, this will return partial derivative of the above function with respect to x when you will enter. So this is the required answer. Similarly, if you want to differentiate with respect to y, then enter. So this is the partial derivative of the above function with respect to y. If you want to differentiate with respect to z, then use z and enter. So we have, this is the partial derivative with respect to z. Also, if again I am using here PER, this is the partial derivative is equal to, I am using here derivative as we do in the previous function for the first order derivative. Okay, so derivative here I am using function f comma x comma y. So this is the mixed partial derivative. Okay, and when you will enter, then part, print the value, and you can see this expression is in this form converted into the symbolic form. This is the partial derivative with respect to x and with respect to y of the function which we choose at this place. Further, if you want to simplify, this is also very quite simple. Part, then we are using here do it function, do it and bracket, then enter. So this will simplify the above function and return the value. If you have at its place 2, so this will be the second order partial derivative with respect to x, PERT. Okay, and for the simplification you will use do it function, and this is the corresponding result. If you have partial derivative of f with respect to x is 2 times, and with respect to y we have is again 2 times, and with respect to z, then enter PART. So you can see at this place we have a mixed partial derivative, and the total partial derivative we have is 5th order with respect to x 2 times, with respect to y 2 times, and with respect to z 1 time, as we instruct at this place. And further, if you want to simplify, we have to use here do it function. So PART dot do it and enter. So this will be the very long calculation. You can see here after simplifying the above function, we have the required result at this place, and frequently it will return the value. So in this way we can easily use diff function for the ODE and PDE, both type of derivatives. And there are 2 different ways to use this function, and I hope when you will use for the different experiments, this will help you in many ways, and also this will support you in the when you will use in Python. Now we will use this SymPy live shell for the integration. To integrate any function, there is inbuilt function in the Python, integrate. This function will integrate the function. I am choosing here very simple example, sine x, and we want to integrate this sine function with respect to x. Then enter. So you can see at its place the integration of sine x is minus cosine x. Similarly, if you have product exponential function and you want to integrate, then just you need to enter. So this is the very simple example I choose at its place for the integration. Now if you have the function f is equal to, we are choosing here sine x square, then cos x, product cos x. This is the function, and if you will print, then this will return the above function in this form. Now if you want to integrate this function f with respect to x, and then enter. So this is the required integration of the above function which we choose at its place, and this is the corresponding result after simplifying. The another way to integrate any function we have is, this is int, we are choosing here expression. Expression is equal to, we have is sine x into exponential function x. Then we have int is equal to integral, sorry, we are using here integral, and then we have expression comma x. So when you will enter this statement, then again use the int and enter. So the this is the same as we do for the derivative. This will convert the expression into the symbolic form. So this is the syntax in Python, and when you will enter, this will print in the symbolic form. So when you will print in the symbolic form, you will use integral. If you want to simplify directly, then you will use the function integrator. There are two different ways. Further, if you want to simplify this integration, then you will use int.doIt function. This will simplify the above integration, and you have the corresponding result. Similarly, if we have definite integration, then what we do, we have, for the definite integration, we will use here x comma, we have, this is the lower limit and this is the upper limit. Suppose that upper limit we have is 1, and then enter. Int, then we have when you will enter, you can see the above this expression, and if you want to further simplify, then use int.doIt function, doIt function, and then enter. So this is the corresponding result after simplification. We are choosing the expression is equal to, we have is exponential of minus x, and enter. Okay, then we have integration of int is equal to integral. Here is, we have expression which we use here, comma. Note this assignment variable which we use for this function. Okay, so expression, then we will have the limit of this integration is 0 to infinity. So we want to integrate with respect to x, and the limit of x we have is 0 to infinity. For infinity, you will use here two times in lowercase. When you will enter, this is the statement has been entered at its place, and you can see there is no error. If our statement will be incorrect, then it will return some error. Now if you want to print this value, again use int. So when you will use int, this is the information which we put at its place, store and the assignment variable int we are using, and for the printing we will again use int at its place. The above expression will be converted into the symbolic form. Further, if you want to simplify this expression, then use int along with the do it function, dot do it and bracket, then enter. So this will simplify the above expression, and the value of this expression we have is 1. Similarly, you can choose one more expression. We have expression is equal to exponential minus x square minus y square. Here we have two variables, then enter. So this is the function which we choose at its place, and if you want to print, then you will again enter expression. Now there are two different ways to integrate this one, and the limit of x and y both are from minus infinity to infinity. Okay, so first we are using here integrate function, then use at its place expression, then the limit of x we have is minus infinity to infinity, and that of y we have is again minus infinity to infinity, then enter. So this will return directly the answer of the above expression. The another way you can use int is equal to, int is again new assignment variable, and we are using here integral. Then we have expression, comma, we have this limit which we use at its place, copy and enter at its place. So the limit of x we have is minus infinity to infinity, and again that of y we have is minus infinity to infinity, and then enter. Int. So the above expression is in the symbolic form is here. First integral minus infinity to infinity, second is also from minus infinity to infinity, e raised to power minus x square minus y square dx dy. So this is the double integration, and definite also. If you want to simplify, again we will use int dot do it function is there for further simplification, and when you will enter, you will get the answer which is same as we find for the first statement. So the answer for this statement and as well as for this statement both have the same answer, because we have two different ways for both type of computing. So in this way we can use SymPy for integration, definite as well as indefinite, whether it is a single integration, whether it is a double integration, and also we can use the same for triple integration, which we will use when we start Python. We can use SymPy for the limit also. Just we need to follow the instructions and need to understand the syntax for limit. We have limit is an inbuilt function, and we are choosing here sin x upon x. So this is the function, and we want to take the limit for this function as x approaches to 0, x comma 0. So this is the corresponding limit for this function, and make the correct function. This is limit. Okay, then enter. So when you will enter, you will find that the limit of this function is 1. The another way to use this function we have is we have expression is equal to limit. here I am using L is in uppercase. Okay, note this point very carefully. And the function we have is again same. I am choosing sin x upon x for the understanding. Once the concept are very clear, then you can choose for different examples. So the limit we have is x approaches to 0. So this is the limit, and then enter. Again use expression for the printing value. So you can see we insert, this is the syntax in the Python, and on the left hand side expression, the input which we give here, limit sin x upon x with the limit x equals to 0. Okay, so where all the information on the right hand side stored in expression. When again you will enter expression, this will print the above statement in the form of a symbolic form. So you can see here, this is the corresponding function in the symbolic form, which is limit x equals to 0 from right side and sin x upon x. Further, if you want to simplify, we will use here do it function as we use for derivative and integration. Do it, then enter. So you can see we have the corresponding limit. Also, if you have the expression is equal to x square, then divide by exponential function. Divide by exponential function, and then enter. Expr is equal to, this is the function x square into e raised to power minus x, and we want to find out this limit. The limit of this function, first we have the function which is expression, then x is approaches to infinity. Okay, this is infinity, O2 times in lowercase, then enter. So the limit of this expression we have is 0. The another way to use this expression, you can use here lim is equal to, and you can use here L in uppercase. Okay, then enter, and lim is equal to, you can see this is the in the symbolic form, and further it's a simplification, you will use here do it function, then enter, and we have the result. Also we can calculate left limit and right limit of the function. Suppose I have a function is equal to 1 upon x. I am choosing here the function is 1 upon x. Okay, if I want to take the left limit of this expression, this is left limit. This is the assignment for the left limit I am using here, is equal to limit, then I have a function which is fun, and limit, left limit for this one will be is x comma 0, then in the quote sign you will use here minus. This is used for left limit. Okay, then enter. Again enter left limit, and when you will enter, this is the symbolic form for the left limit. Further, if you want to simplify, then left limit dot do it function is there, and this will simplify the above expression which is minus infinity. In the same way we can use for right limit. Here is right limit. This is the assignment variable. You can take another form or any assignment variable, but I am choosing here right limit for right limit. Okay, here is limit, then I have function fun comma x approaches to 0. This is the limit from right side, use here quote sign, and for the right limit we are using here positive sign, then enter. The statement has been entered and all the information on the right hand side stored in right limit. Okay, again if you want to print this value, then you have to enter the assignment variable. This will print the value, and this is the required expression in symbolic form. For the further simplification, we will use here right limit, then do it function, and this will simplify the above expression. So this is the required value, and you can see left limit and right limit both are different, so limit are not equal. By employing SymPy, we can harness its capabilities for differentiation, integration, and limit calculations. I trust that this lecture will prove beneficial to your computational endeavors. Thank you for staying with us until this conclusion.